We've reached Module 11, and this is kind of what I like to think of as the home stretch of the course. And it's perhaps useful to take a look back and see essentially where we've come from. Remember, in the very beginning of the course, we were essentially learning about naked eye astronomy, why the sky moves the way it does, why the moon has phases, all that kind of stuff. Then we took a little detour and we learned about the sun, we learned about light, we learned about the sun, and essentially how our solar system came to be. And then we put our sun, all that stuff is still pretty close to us, right? It's pretty close to home. Then we talked about how the sun compares to the other stars, and particularly the stars in our own galaxy, the Milky Way galaxy. We talk about the evolution of stars, that they do indeed go through life cycles. They are formed, they spend a long time on the main sequence, and then they die in various ways, quite often winding up as either white dwarfs or neutron stars, black holes. We talked about supernovas, all that kind of stuff. Now, we are going to climb the cosmic distance ladder. In fact, that's the title of the lab activity you're going to be doing with this module, because we're going to now learn about stuff that's not just within our own Milky Way galaxy. We'll talk about the Milky Way galaxy. In fact, chapter 17 is about the Milky Way galaxy. And we'll learn how astronomers figure out the distances to objects within our own galaxy, as well as we're going to learn how astronomers find the distance to galaxies outside of our own, because it turns out that 100 years ago, when we were just barely discovering that we were in a galaxy, it was thought that Milky Way galaxy was it. But it turns out, as we've learned as technology has improved, we've had better telescopes, that our galaxy is just one among billions of galaxies out there. And so we're going to learn how astronomers determine the distance to these different galaxies. We're going to learn the properties of some of these galaxies. That's the topic for chapter 18. So, like I said, a lot of ground to cover in just 2 chapters. Okay, so if you've ever been observing the night sky, especially in a dark location, you have seen the Milky Way. It's essentially that milky-ish patch through the sky, or that band through the sky, that is seen from a dark location. And it's essentially the collected light from all the stars that are in our particular spiral arm of the Milky Way galaxy. But one thing that's really important for you to understand is that when you look up in the night sky with the naked eye, you are just seeing stuff within our own galaxy, with the exception of one object. You may see a very small fuzzy patch in the constellation Andromeda. What you're actually seeing there is an object that is outside our own galaxy. It's a relatively near neighbor called the Andromeda Galaxy, M31. And this is the only thing you can see with the naked eye that does not belong to our own galaxy. It's actually outside our own galaxy. It's a galaxy unto itself. So what looks like a little fuzzy patch in the sky to the naked eye actually is the collected light of 100 billion or so, 200 billion stars that make up the Andromeda Galaxy. It's sometimes said that we know less about the oceans or the interior of the Earth than we do some of our nearest neighbors in space, like the Moon or Mars. And that's partially true, because it's really difficult to go to the bottom of the ocean and explore. It's even more difficult to go into the interior of the Earth and explore. It's a little bit easier to kind of send a probe out and perhaps look back at the Earth or look at the Moon, that sort of thing. Same issue with the Milky Way galaxy. We know less about the actual structure of our Milky Way galaxy than we do, some other galaxies, because we are in the Milky Way galaxy. That's a little bit more difficult. We've never sent a probe out far enough to turn around and take a selfie of our galaxy. In fact, we've barely sent our farthest probe is just outside of our own solar system. I remember that would be like the Voyager probes that were launched back in the 70s. They've barely gotten out of our own solar system, much less gotten out of the Milky Way galaxy and been able to turn around and take a selfie and then send that information to us. Remember, that would have to be a trip of hundreds of thousands or 100,000 light years or so in order to really encompass the entire galaxy. So anyway, that's part of the problem, is that we're inside. So we can't get an overall view of the Milky Way galaxy the way we can, say, the Andromeda galaxy, because we're outside of the Andromeda galaxy. We can see the entire thing. Another difficulty is that there's a lot of gas and dust, so it's tough to see the center of the galaxy. And another difficulty is distance measurements. But one thing that we're really going to be focusing on this module is the different tricks that astronomers use to determine the distances to objects. And again, like I said, that's the theme of the lab activity for this module, is the cosmic distance ladder. We'll climb the cosmic distance ladder using different techniques to determine the distances to objects, not only within our own Milky Way galaxy, but also to distances to other galaxies. Again, it never ceases to amaze me the physics that goes into astronomy. So one way of determining the distance to objects is to observe, and especially to determine the distance to other galaxies, is to use what are called Cepheid variable stars. These are stars that don't stay the same brightness. They tend to vary in their brightness, and that's what we're seeing here. We're seeing the light curve, the visual magnitude. So this is essentially how bright these stars appear from Earth. And this particular star does vary in its visual magnitude. But the nice part is that it varies in a consistent way. Over this time period, it goes from being its dimmest to its brightest and back to its dimmest. And that's nice because once we're able to determine that period, it turns out that the period of a variable star like this is related to its luminosity. And once you know the luminosity, remember luminosity is essentially absolute magnitude. Once you know the capital M, and we already know the little m, once you know those two things, you can determine the distance by using what's called the distance modulus. And again, we'll get practice using that equation. It's not something you have to memorize, but it is useful in determining the distance to, in this case, the star. And of course, the star is just located within a galaxy. So if you know the distance to the star, you know the distance to the galaxy. So as I already mentioned, we don't have a selfie of the Milky Way galaxy. So how do we know what it looks like? Well, it's kind of like if you don't have an overall picture, but you can start to fill in some of the pieces, it starts to take shape. And that's the way essentially astronomers do it. They first of all try to find bright objects and use different techniques to determine the distance to those objects and their directions of motion. They can use also different wavelengths outside of the visible, because with visible you do get a lot of gas and dust that gets in the way and blocks visible light. So that's another strategy for determining the distance and direction of other objects. And once you've started to find out those distances and the directions of motion, the overall picture begins to take shape. Even within a galaxy, you'll find clumps, essentially, of stars. Some are closer packed than others. And when you have a lot of packing of stars, we call those clusters. And there's two different types of clusters, open clusters and globular clusters. Open clusters are not as dense. There's not as many stars per unit volume in an open cluster compared to a globular cluster. And it turns out that open clusters tend to, at least in the Milky Way galaxy, and we assume in other galaxies as well, they tend to be within the disk of the galaxy. So when you find open clusters, they typically are within the galaxy's disk. When you start to find globular clusters, they tend to be outside of the disk area and more in what's called the halo. Now, if you ever get a chance to look through a telescope, I encourage you, whoever's operating the telescope, to check out the double cluster. The double cluster is in the constellation Perseus, and it's a good example of open clusters. You actually have two open clusters relatively close together. So what looks like to the naked eye just kind of a fuzzy patch in the sky, when you put a telescope on that fuzzy patch, you're going to see hundreds of stars popping into view, which is really quite breathtaking. Now, I sort of put the cart in front of the horse in the last slide by mentioning the fact that the center of the galaxy is in essentially in the constellation Sagittarius. How do we know that? Well, it turns out that Shapley, who did a lot of the research on star clusters, particularly globular clusters, when he started to plot them, realized that the globular clusters are not distributed evenly around the sun. In fact, they're distributed evenly around a different portion of the Milky Way galaxy, and that's how he determined that that location must be the center of the Milky Way galaxy. And it's essentially, like I said, in the constellation Sagittarius. It is very difficult to research it using visual observations, because when you're looking toward the center of the galaxy, you're looking through not only billions and billions of stars, but all kinds of gas and dust and that sort of stuff that obscures the view. So quite often researchers have to use different forms of radiation in order to to peer into the center of the galaxy. Okay, so now we're finally getting a pretty good feel for the structure of the Milky Way galaxy. First things first, the size of the Milky Way galaxy. You're going to see varying numbers for this because there is no real definite boundary. It's kind of like, asking, where does the solar system end? Or, there is no marker out there in space saying you're now entering the Milky Way galaxy, you're now exiting the Milky Way galaxy. You're going to see values anywhere from 75,000 light years in diameter to upwards of 100,000 light years in diameter. Notice where the sun is located. We're about 2/3 of the way out from the center of the galaxy. So we're not necessarily at the center of things. We're a modest distance out. We are located along the disk of the galaxy. Remember, we talked about the fact that we have the disk of the galaxy, and then you have the halo section of the galaxy. So we are in the disk. We're actually on a spiral arm of the disk. And as mentioned already, most open clusters occur in the disk part of the galaxy. Globular clusters tend to be located in the halo portion of the galaxy. And one thing that makes a galaxy is, remember, a galaxy is just a collection of billions of stars, and they are gravitationally bound to a center. So there's a galactic center. We say it's in the vicinity of the constellation Sagittarius, and all of the stars appear to be bound to this galactic center, and they orbit around. Well, it turns out that our sun takes about 240 million years to orbit one time. So if you recall, our solar system is about 5 billion years old. So that means that we've been around the track about 20 times or so in the lifetime of the solar system. Another thing that's relatively interesting about the motion of the stars in the Milky Way galaxy is, well, first of all, think about the orbits of the planets in our own solar system. Which one orbits fastest around the sun? Mercury, right? We saw that, and in fact, Kepler figured out the fact that as you get farther and farther away from the star, in this case our sun, the longer it takes for that planet to orbit. And so you would expect that stars that are close to the galactic center should be moving very, very quickly, and stars that are moving farther away from the galactic center should be moving much more slowly. That's what you would expect. Flip the page to find out what's the reality, the reality of the situation. Okay, so as I mentioned, you would expect when you start to plot the velocity of stars with respect to their distance away from the center of the galaxy, you would expect to see this kind of a relationship, the Kepler kind of relationship, where as you increase the distance, the star should be moving slower. In reality, with the measurements that have been taken, you actually see this curve here, which does not show that decrease in velocity with distance from the center. So it turns out that stars in the Milky Way galaxy do not behave according to what Kepler would expect, and that means that there must be something else going on. There must be some sort of other gravitational force apart from just the gravitational attraction of the center of the galaxy at play here. There must be mass, there must be matter that we have a hard time detecting, which is influencing the orbital velocity of stars. And it turns out this winds up being dark matter, which we'll have more to say about in the next module. And then actually, it should be noticed, a huge surprise that all stars are not the same age. But how do you age? How do you determine the age of a star? Well, one way of doing it is by looking at the absorption spectrum of the star and seeing its composition. Because it turns out that stars that are made up mostly of hydrogen and helium have got to be old stars. They must have been made early on in the universe. Shortly after the Big Bang, when the Big Bang first occurred, all that was around was essentially hydrogen and helium, mostly hydrogen and a small amount of helium. And that's what the first stars were made from. And so if you have an absorption spectrum from a star like that that is made of just hydrogen and helium, it shouldn't have much in the way of any other absorption lines apart from hydrogen and helium. Stars that were made late, now of course those are early stars, especially the ones that had short lives, those really hot ones that lived fast and died young, when they exploded, when they went supernova, they spewed their enriched guts. Remember, we've talked about the fact that as a star goes through its dying process, it generates other elements beyond hydrogen and helium. And that is what in astronomy we call them metals. So anything heavier than helium is considered to be a metal. And so it spews its enriched guts, which include metals heavier than helium, into the interstellar medium, from which new stars are created. So that next generation of stars will have hydrogen and helium, but they'll also have small percentages of those heavier elements. And the more generations that occur, the more enriched the interstellar medium becomes. And so the younger a star, the more recently a star has formed, the more you would expect it to have metals as part of its composition that would be picked up in an absorption spectrum. So population 2 stars are your really old ones that are what are called metal poor. They're mostly hydrogen and helium. Population 1 stars are recently formed stars that were formed from interstellar medium that had the enriched guts of generations of stars that had exploded before as part of the interstellar medium. So population 1 stars, you would expect to be metal rich. Okay, so one thing we've discovered is that the Milky Way galaxy is what's called a spiral galaxy. We'll talk more about the different types of galaxies in the next chapter, but for the time being, let's just think about why we have these spiral arms that make up the Milky Way galaxy. And it turns out that, of course, the spiral arms are areas where there's a lot of stars, in fact, new stars, very, very bright stars are showing up. And those stars are, of course, forming from gas and dust. That's what stars come from. So there must be something that's triggering gas and dust to become stars in these spiral arm areas, as opposed to other parts of the Milky Way galaxy. We'll talk about that on the next slide. Okay, so I encourage you to check out page 381 in your textbook to explain why we have spiral arms. There's a theory called the spiral density wave theory, and I encourage you to check that out, that description on page 381. But one way of thinking about why stars appear to form in these spiral arms is to think about like a traffic jam. Like if we were looking from above, seen from an airplane, a traffic jam would look quite stable. You're seeing cars slowing down, just moving down the highway. The individual cars in the jam would constantly be changing, but the traffic jam would be essentially a stable pattern moving at its own speed along the highway. If you've got this tractor, it's going to continue to move, and cars are going to continue to jam up behind it, and then they're going to move, they're going to zip around, and so the jam will always be there, but the cars that are participating in the jam will be constantly changing. And that's essentially what's happening in these spiral arms, is that the gas and dust is actually rotating faster than the density wave. But as that gas and dust moves into that density wave, it's like having that shock wave that's able to spur star formation. So the gas and dust is just gas and dust, but it gets triggered when it moves into these density waves to actually start forming stars. And of course, the stars that are the ones that the hottest ones are the O's and B's. Those are the ones that are easy to see, and they also live very short lives. So it's indicative of spiral arms that they are indeed star-forming regions, because you see old stars distributed throughout the entire disk of the Milky Way galaxy, where the O's and B's are seen is only in the spiral arms themselves, because O's and B's have relatively short lifetimes. Okay, so we've talked about the structure of the Milky Way galaxy and the fact that our solar system is in a spiral arm of that galaxy. We haven't talked too much about the center, because we've already said that it's kind of tough to see the center because there's so many stars, there's so much dust, there's so much gas in the way. So you use radio telescopes, you use other types of light to probe, to peer into the center of the galaxy. So what's at the center of the galaxy? Right now, the best theory is that there's actually a black hole at the center of the galaxy, and not just any black hole. It's a black hole that is very, very massive. Again, we see the motion of not only the galaxy as a whole, but also, in particular, the motion of the stars and objects close to the center of the galaxy. And that the motion of those objects indicates that there's got to be something really massive that's causing these to move in the way they do. In fact, these are some of the motions of an object called Sagittarius A with a little asterisk there. That thing has been tracked with our telescopes, and the only way it can move the way it does with its mass is that there's got to be a 2.6 million solar mass black hole at the center of our galaxy. Okay, so we've been talking mostly again about stuff in our own galaxy. We just talked about the center of our galaxy. Let's talk about stuff outside of our galaxy. And the way you can best understand this little slide here is by first of all paying attention to down here. That's the Big Dipper, right? An asterism we're all familiar with. Well, the director of the Hubble Space Telescope, that wonderful feat of engineering, decided to point the telescope, the Hubble, in this part of the sky. It's a pretty empty part of the sky, not a whole lot of stars in that particular field. And he said, let's just point Hubble in that direction and just let it stare for like 10 days. Let's see what it picks up. And what you see up here is what Hubble managed to pick up. Not a whole lot of stars, right? In fact, here's one, here's two, let's see, any more? There's another one, there's three. There's about 4 stars in this, oh, here's another one, there it is. About 4 stars from within our galaxy that show up in this particular part of the sky. Everything else that you're seeing here are galaxies unto themselves. So this apparent empty patch of the sky wound up producing, gosh, one of those dozens, maybe hundreds of galaxies. And they're various shapes. There's a couple of spiral galaxies in here. There's some elliptical galaxies, and we'll talk more about these in coming slides. You've got irregulars showing up, but the important thing is this apparently barren piece of sky is actually very, very rich in galaxies. So if you imagine just this little segment of sky producing this many galaxies, and then assume that if you looked in any other direction and did the same thing, just let Hubble stare, you'd wind up with something similar. That gives us a feel for how many other galaxies are out there. So our star, our sun, is just one of perhaps 100 billion or 200 billion stars in our galaxy. And it turns out that our galaxy is one of billions and billions of other galaxies out there. Just remarkable. I encourage you to check out the 2-page spread on pages 398 and 399 that pretty much goes along with this particular slide about galaxy classification. So some galaxies are considered to be elliptical galaxies, some being more elliptical or more oval than others. So elliptical galaxies are classified with the E, but then they also go from anywhere from 0 to 7, 0 being the most spherical, the most round, to 7 being the most out of round. Then of course you have spiral galaxies, and you can see why they're called spiral galaxies, because they all look like spirals with these spiral arms. And they go anywhere from what's classified as an S with an A beside it, being a rather large nucleus and very tightly wound arms, to the C classification, which means it's a very small nucleus with more loosely wound arms. Okay, I'm not going to say too much about distance measurement. It is covered on pages 400 and 401. Pay particular attention to the term standard candle. But you're going to be learning a lot more about this in this module's lab activity, which is the cosmic distance ladder, the different techniques that astronomers use to determine distances to objects, not only in our own galaxy, but the distance of entire galaxies from Earth. Now, it's one thing to know the distance of objects from the Earth. It's another thing to know the velocity of those objects. And in the early 20th century, astronomers were compiling all this information, and a guy named Edwin Hubble finally plotted all this stuff, all this information. And when he started to plot the distance of galaxies and their recessional velocity, the velocity away from the Earth, it turns out that he came up with a very important discovery, which was that the farther a galaxy was from the Earth, the faster it was moving. Essentially, the universe was expanding, but not expanding, essentially expanding faster the farther away you get from the Earth. That's pretty significant. And so he wound up developing this thing called the Hubble's Law and the Hubble constant. Okay, this discussion of clusters of galaxies starts on page 406, continues on to page 407. But essentially what it's saying is that galaxies, kind of like stars, don't often exist alone. Usually you don't have stars that are cosmic loners. Similarly, galaxies quite often wind up clustering. And there's a distinction described on these two pages between rich clusters and poor clusters. Okay, so this is our cosmic hood, as it were. These are our cosmic peeps. Of course, we have this diagram is on page 407 of your textbook. Milky Way galaxy is the center here, just because we're rather egocentric. But to give you a feel for how much space this diagram encapsulates, the radius of this sphere here is 500 kiloparsecs. And so notice that we do have a couple of neighbors nearby. We have a couple of irregular galaxies called the Small and Large Magellanic Clouds. We also have the Andromeda Galaxy here, M31, which, again, if you've ever seen it with the naked eye, it's the farthest thing you can see with the naked eye in our night sky, unassisted. Usually you have to look from pretty dark skies, but it is 2.5 million light years away. And that galaxy is actually on a collision course with our galaxy. Eventually they should collide in about 5 billion years. One thing I should clarify is that though distant galaxies are indeed receding, getting farther away from us, from the Milky Way galaxy, that's not necessarily true of our local group. So if your galaxy is close enough to you, it may not be receding. You may be gravitationally bound to each other, and that's how groups are formed. That's how these clusters of galaxies form. So even though distant galaxies are moving away, your neighbor galaxies quite often are gravitationally bound to you, and therefore quite often they wind up interacting. And there's a whole pull out here, a two-page spread on pages 410 and 411 of your textbook, which discusses concepts like mergers of galaxies and even galactic cannibalism. Okay, the remaining material comes mostly from chapter 18, and it has to do with active galaxies. Now, what is an active galaxy compared to a non-active galaxy? Well, we've seen pictures of just galaxies, whether it's the Andromeda Galaxy, we've seen images of our own Milky Way galaxy, and remember that galaxies are collections of stars that are essentially gravitationally bound to each other. And in a galaxy, they're usually bound to a central object, a nucleus. And it's thought that at the heart of most galaxies is a supermassive black hole. That's what's holding all these stars into this pattern we call a galaxy. But most of these galaxies are not super bright. We can certainly see the Andromeda Galaxy, even with the naked eye, as a little smudge. But there are certain galaxies that have a lot of light, that are producing a lot of light, particularly in the center, in the nucleus. And those are what are called active galaxies. In fact, the nucleus, that center, is called an active galactic nucleus, an AGN. There's a lot of energy being released. And the question is, why, what's going on there. Clearly, there's got to be, if there is a black hole at the center, there must be material falling into the center that is being heated up and producing a especially energetic type of light, X-rays, gamma rays, etc., etc. In order that that nucleus is actually producing way, way more light at the center than our entire Milky Way galaxy might be producing. And so that this whole section in chapter 18 talks about how you can distinguish active galaxies from your more passive galaxies, from your average galaxies. And so there's a whole section on Seyfert galaxies and their properties. There's actually two different types of Seyfert galaxies. One thing that is also something that's worth paying attention to is the fact that you wonder, well, where is all this material that is falling in coming from? And it turns out that a lot of astronomers think that it's the result of interacting galaxies. Quite often, your active galaxies are ones that are somewhat distorted. And that's most likely because they are the result of some collisions between galaxies. And that collision allows for a lot of material to fall inward toward the center of the galaxy. Galaxies like our own Milky Way galaxy have kind of reached a sort of steady state. You know, the stuff that was close to the center has fallen in already, and there's not a whole lot of new material falling inward into the center. And therefore, we are not considered to be an active galaxy. We may have been at one time, but our active days are long past. You know, kind of maybe your tumultuous teenage years are when you would be considered an active galaxy. Now we're kind of a middle-aged or even a more of a senior citizen type of galaxy, and not a whole lot is happening at the center. But again, all these radio lobes and cosmic jets are symptomatic or symbolic of active galaxies. Okay, so unlike Seyfert galaxies, where most of the energy is occurring at the core, radio galaxies, a lot of the energy being received here on Earth is coming from lobes or jets that are kind of placed pretty far away from the core. And again, the reason why radio is very useful is that, first of all, radio wavelengths, as you recall, can actually be received here at the surface of the Earth. You can build a radio telescope that can pick up this type of light, whereas other types of light, you know, we've discussed the opacity of the Earth's atmosphere, that really on the Earth's surface, visible telescopes and radio telescopes are the only ones that can be built because none of the other stuff gets through. So radio is very useful because, first of all, it can be received here at the surface of the Earth, and also because radio waves can travel long distances in space without getting blocked by intervening material. So these radio galaxies can be picked up. And again, these are radio wavelengths, despite the fact that this is, you know, very hot stuff. You know, these lobes, these jets are still ionized or very energetic electrons, but quite often these are also from very distant galaxies, and so even though it's very energetic light to begin with, it becomes redshifted to the point where it winds up in the infrared or down into the radio wavelengths. So these radio galaxies are very useful in being able to study relatively active. You know, you wouldn't have these lobes or jets without having an active center. But the center is not that visible, but the radio lobes are. So that's why we have these radio, what are called radio galaxies. Okay, so you probably read in the book about a push in astronomy for a unified model. There's a lot of thought that these various active galaxies, whether it's just an active galactic nucleus, whether it's a Seyfert galaxy, whether it's a radio galaxy, or these radio lobe galaxies, or double lobed radio galaxies, they all may be essentially born out of the same processes, and that we may just be seeing them from different angles. We may just be seeing them at different life stages. And so one thing that's pretty common is that you have these accretion disks and even what's called a torus, kind of a donut-shaped area of gas and dust. and it's pretty clear how the accretion disk forms. One thing that's not really clear is the physics behind the formation of these jets. And yet the jets are pretty common with these different types of galaxies. So again, the push for unification, or this unified theory, is that a lot of these have similar characteristics. And so perhaps they're all forming using the same processes. There just may be differences in scale, maybe differences in what part of the life of the galaxy we're actually viewing. And here's a view of a torus, a dust torus, again, that donut-shaped area of gas and dust that a lot of that material winds up falling in and creating your lobes or your jets. Quasars are the next topic of study, and again, these are active nuclei, and these are from very, very distant galaxies. These are very bright galaxies, but they're also very distant galaxies. And we can see that because of the large amount of redshift that's going on. That tells us that these are very, very distant galaxies. I mentioned the quasars have these huge redshifts. In fact, the redshifts would appear to be impossible, that making the quasar actually move faster than the speed of light, but we must keep in mind that these are so distant that these are, the quasars are actually being subject to the very rapid expansion of space itself. It's not that these quasars are moving this quickly through space, but rather that space itself is becoming larger, is growing, and that's where we get into what's called relativistic effects. Okay, so quasars, again, they were called quasi-stellar objects because they are very distant. They are known to be galaxies, but they're very, very bright. You wouldn't expect them to show up the way they do at such large distances. They actually show up like stars, even though it's the light from a galaxy, and that's because of that very active nucleus of the quasar. So here's an example of what a quasar looks like compared to a galaxy. These are actually two images of the same quasar. What's going on here is we actually have what's called gravitational lensing, where the light is being bent around a galaxy. The light from a distant quasar gets bent by the gravity of the galaxy, and so therefore we wind up with two different images of the same quasar, and there's the galaxy that's doing the bending. It's a process called gravitational lensing, which actually shows us that light indeed can be bent by large masses as it travels through space-time. And again, here's a little gallery of quasar galaxies.